We are currently drifting through a colossal, almost incomprehensible expanse of space. This cosmic emptiness spans approximately 2 billion light-years from one side to the other. It is a staggering thought, an idea that most individuals have simply never encountered. Scientists confirmed its existence back in 2013, yet this discovery remains largely unknown to the general public. We are living within what is now called the KBC void. It is essentially a cosmic desert, a region where the typical amount of matter is 20% thinner than what we would expect to find in an average section of the universe. This profound absence of density, this vast hollowness, is subtly distorting our very measurements of reality itself. Here, within this enormous bubble, the universe appears to be expanding at a noticeably faster rate than it does elsewhere. This accelerated expansion, observed from our specific vantage point, challenges our most fundamental equations, the very principles we use to describe the cosmos. Tonight, we will embark on a journey into this remarkable discovery, a revelation that has quite literally shaken the foundations of modern cosmology. We will uncover the reasons why roughly 90% of all space is largely hollow, and we will ultimately explore what it genuinely signifies to exist on the distant cosmic outskirts of the universe. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Our story of this vast emptiness began with a meticulous count performed by 3 dedicated astronomers. Ryan Keenan, Amy Barger, and Lennox Coey, in the year 2013, undertook the monumental task of examining tens of thousands of galaxies. They carefully mapped the precise locations of 35,000 distinct galaxies, extending their survey across billions of light-years of cosmic distance. As they compiled their findings, a startling realization slowly began to dawn upon them. The numbers they were observing simply did not add up. They were, in fact, demonstrably incorrect. Everywhere these researchers looked, within the local universe, particularly in the vicinity of our own planet, they consistently found a significant scarcity of galaxies. There were, quite simply, fewer galaxies present than their cosmological models predicted there should be. This wasn't a minor deviation, a slight statistical blip in the data. The deficit was substantial, a pronounced 20% reduction in the expected galaxy population. This peculiar pattern, this widespread scarcity, radiated outwards in every conceivable direction from our location for an astonishing 1 billion light-years. It manifested as an immense spherical region of cosmic emptiness, with our solar system situated remarkably close to its very heart. This was no ordinary gap, not merely one of the small, expected spaces that naturally form between clusters of galaxies. This was an astronomical void on a scale so utterly monumental that its mere existence seemed to defy the established tenets of standard cosmology. Such a vast, underdense region should, by all accounts, simply not be there. The researchers understandably approached this anomaly with extreme caution. They meticulously triple-checked every single piece of their data. They cross-referenced their findings with multiple independent galaxy surveys, ensuring the robustness of their observations. They even scrutinized the celestial sphere from a myriad of different viewing angles. Yet, despite their exhaustive efforts, the astonishing result remained stubbornly consistent. Our own galaxy, the magnificent Milky Way, along with everything surrounding it, was unquestionably embedded within an enormous, underdense bubble of space. This bubble, this region of diminished matter, was so incredibly massive that it dwarfed every other celestial structure we had ever previously observed. The profound nature of this unprecedented discovery eventually earned it a name. It was called the KBC void, using the initial letters of its 3 persistent discoverers. While the name itself might sound unassuming, almost casual, there is, most certainly, nothing ordinary about what it represents for our understanding of the entire cosmos. The standard model of cosmology, often referred to as the lambda CDM model, operates under a foundational principle. It posits that when one zooms out far enough to observe the universe, on truly grand scales it should appear roughly uniform. This means that the distribution of matter, the arrangement of galaxies, should be approximately the same everywhere you look. It's perfectly normal, of course, for galaxies to clump together, forming clusters, and for empty spaces to naturally exist between these gatherings. That kind of localized variation is entirely expected and accounted for. However, a region of space, as incredibly enormous as the KBC void, exhibiting such a significant and widespread deficit of matter, pushes the absolute boundaries of what random chance alone can realistically explain. Consider for a moment the intricate workings of computer simulations. These sophisticated models are designed to replicate how the universe has evolved since its very inception with the Big Bang. They show us how initial tiny irregularities in the early universe gradually grew under the influence of gravity to form the vast structures we observe today. Yet, even in these advanced simulations, supervoids of this particular size and this profound emptiness are exceedingly rare occurrences. When such extreme voids do happen to emerge within the simulations, it typically necessitates exceptionally unusual and highly improbable initial conditions in the universe's primordial state. The statistical probability of such an event is extraordinarily low, often calculated at less than 1 chance in 1,000. Some meticulous scientists have even gone further in their calculations. They suggest that the KBC void's underdensity represents what is known as a 10 sigma deviation from the average cosmic density. To put that into perspective, a 5 sigma deviation is typically considered the gold standard for a scientific discovery, meaning there's less than a 1 in a million chance it happened by random variation. A 10 sigma deviation is so incredibly unlikely, so statistically improbable, that you might not expect to find even a single void of that magnitude within the entire observable universe. And yet, here we are. We find ourselves, quite literally, residing inside one of them. The moment this astonishing discovery was confirmed, its implications began to ripple outwards like a cascade through the entire field of cosmology. A crucial and deeply uncomfortable question immediately arose: if our home within the universe is such an incredibly unusual location, does that inherent bias subtly influence every single measurement we make about the cosmos? When we meticulously point our powerful telescopes towards distant, exploding stars, known as supernovae, to precisely gauge the rate at which the universe is expanding, are we truly observing the universal cosmic expansion rate, or are we merely detecting a distorted, localized version of that expansion specifically shaped by our unique position? The void hypothesis, remarkably, offered a compelling answer to one of the most perplexing mysteries in contemporary cosmology: the long-standing and increasingly troubling Hubble tension. For several years, scientists have consistently measured 2 distinctly different cosmic expansion rates. One measurement is derived from peering back into the ancient universe, observing the faint afterglow of the Big Bang. The other comes from studying the relatively nearby universe using precise observations of local cosmic beacons. The numbers from these 2 highly precise methods simply do not align. They disagree by a noticeable and significant 9%. This difference, while seemingly small, represents a profound crisis within the scientific community. Both sets of measurements are remarkably accurate, meticulously performed with incredibly small error margins. Both, according to our current understanding, should yield exactly the same result. But they don't. Now, consider this possibility if our planet Earth is indeed situated within a truly massive, underdense region, then the collective gravitational pull from the much denser matter that surrounds the void would exert an outward tug on all the galaxies residing within it. This external gravitational influence would impart an additional velocity, an extra push, to the motion of those galaxies as they recede away from us. This, in turn, would make the local expansion appear to be faster than the actual cosmic average. Suddenly, the two previously conflicting measurements of the universe's expansion began to make perfect and unsettling sense. We weren't necessarily measuring the universe incorrectly. Instead, we were quite literally taking our measurements from inside a gargantuan cosmic whole. This profound realization fundamentally altered our perspective on everything we thought we understood about the universe. But it also immediately brought forth an uncomfortable and still largely unresolved question that cosmologists continue to grapple with. If our specific location within the vastness of space is truly this unusual, this statistically improbable, can we, with any genuine confidence, trust anything we believe we know about the wider cosmos? The subsequent exploration of this cosmic puzzle only serves to underscore just how peculiar and extraordinary our immediate cosmic neighborhood truly is. When astronomers refer to a region of space as a void, it does not imply a complete and utter absence of all matter. The term void in this context simply signifies that the region contains substantially less matter than the average cosmic density. It is, by no means, absolutely empty in the strictest sense of the word. The immense KBC void, which encompasses our own galaxy, for instance, still possesses a measurable amount of cosmic material. It has roughly 15% of the normal cosmic density expected in. Think of it this way. Imagine a typical, average section of the universe where you might expect to find perhaps 10 galaxies within a certain defined volume. If you were to examine that same exact volume within our local void, you would likely encounter only one or maybe two lonely galaxies. These galaxies do not, of course, simply vanish. Instead, they become rare, isolated specks, like scattered islands adrift in an immense and largely featureless ocean of near-nothingness. Between these solitary galaxies, stretching across unimaginable distances, lies space that is predominantly filled with the enigmatic dark matter, the mysterious dark energy, and occasionally, faint, ethereal wisps of hydrogen gas. The overall density within these void regions is so incredibly low that the fundamental force of gravity barely functions in any noticeable way. Without a sufficient concentration of mass to pull things together, the intricate process of structure formation essentially grinds to a halt. No new, grand galaxy clusters can coalesce and form. No rich, sprawling superclusters can emerge from the sparse material. The void, by its very nature, maintains its emptiness, persisting as a void. This profound emptiness, this cosmic scarcity, has far-reaching consequences that ripple through the very fabric of physics itself. Gravity, as we understand it, is already the weakest of the four fundamental forces in nature. It requires truly enormous masses, like planets, or stars, or entire galaxies, to exhibit any significant and observable effects. But inside a void, where mass is extraordinarily scarce, gravity's influence becomes even more diminished, almost irrelevant. In these desolate regions, the dominant force, the ultimate ruler, becomes dark energy. This mysterious and pervasive pressure is the unseen engine that accelerates the universe's expansion. In stark contrast, within dense regions, those crowded with countless galaxies, gravity wages a constant battle against the outward push of dark energy. Here, gravity manages to slow down the expansion in those localized areas, holding structures together. However, inside the vast, empty voids, gravity decisively loses this cosmic tug of war. Dark energy, with no significant opposition, wins hands down. As a direct consequence, voids expand at a significantly faster rate than the rest of the universe. They grow, much like rapidly inflating bubbles, continuously pushing their boundaries outward. Meanwhile, the intricate filaments, those long, thin strands of galaxies that surround these voids, act like colossal, cosmic walls containing the expanding emptiness. This process creates a self-reinforcing cycle. The more a void expands, the emptier it becomes, which in turn allows for even faster and more unrestrained expansion. Scientists have rigorously confirmed this accelerated expansion through careful and systematic observation. They have meticulously measured the movement of galaxies situated near the edges of these voids, comparing their velocities to those of galaxies residing in denser regions. The findings are clear: the galaxies within voids are rushing away from the void's center at speeds that are greater than cosmic expansion alone can explain. Something, quite literally, is pushing them outwards. That something, that unseen force, is the collective gravitational pull emanating from all the denser matter that exists outside the void's boundaries. Imagine, if you will, a deep valley nestled amongst towering mountain ranges. Gravity naturally pulls objects downhill from the peaks towards the valley floor. But in the context of space, rather than literal terrain, that gravitational pull from the surrounding dense matter causes galaxies within the void to fall outwards, away from the void's center, rather than inwards. This effect is not merely theoretical, it is both measurable and profoundly significant. Our very own galaxy, the Milky Way, is currently moving away from the local void at an astonishing speed of 600,000 miles per hour. This rapid outward motion is driven entirely by this gravitational imbalance, a direct consequence of our position within the cosmic emptiness. The interior of a void, therefore, becomes a truly strange and unique laboratory for the laws of physics. Light, as it travels through these underdense regions, experiences considerably less gravitational influence than light that passes through normal, denser space. This subtle difference affects our observations in delicate but measurable ways. When astronomers meticulously study the cosmic microwave background radiation, that faint, ancient afterglow of the Big Bang, they notice a peculiar effect. Light that has journeyed through vast cosmic voids appears to be ever so slightly cooler. The reduced gravitational pull within these voids causes less gravitational redshift, a phenomenon that manifests as distinctive cold spots in the precise temperature maps of the early universe. Remarkably, these cold spots align perfectly with the locations where we currently observe large cosmic voids. This alignment is not a mere coincidence. It is, unequivocally, a fundamental principle of physics in action. Understanding precisely what makes voids so empty helps us to grasp why they hold such profound importance for the field of cosmology. They are not simply boring, blank spaces between the more interesting galaxy clusters. On the contrary, they serve as vast, natural laboratories where the mysterious dark energy utterly dominates and where the force of gravity takes a decided backseat. By meticulously studying how matter behaves differently within these voids compared to its behavior in dense regions, scientists can rigorously test fundamental theories about how the universe actually operates. The KBC void, the colossal emptiness surrounding us, might admittedly be unsettling because it forces us to question our cosmic typicality, our assumed ordinariness within the universe. But paradoxically, it also presents a truly rare and invaluable opportunity. We are positioned, quite literally, in precisely the right place to undertake an in-depth study of the universe's most extreme, low-density environments. The overarching structure that actually contains these vast voids is far more intricate and perplexing than anyone had ever previously imagined. The universe, as we now understand it, is not a smooth, homogeneous soup of evenly distributed galaxies. Instead, it bears a striking resemblance to Swiss cheese, where dense clumps of matter form vast, interconnected walls and intricate filaments, which in turn encircle enormous, hollow pockets of emptiness. This foam-like or sponge-like architectural arrangement is known as the cosmic web, and it represents, quite literally, the largest and most grand structure in all of nature. Massive galaxy clusters, those brilliant nodes of intense matter density, tend to concentrate at the crucial intersections where multiple filaments converge and meet. These nodes are truly spectacular, shining brilliantly, with millions of galaxies packed relatively close together in a vibrant cosmic dance. Stretching out between these luminous nodes run the filaments themselves, long, sinuous chains of galaxy groups that can extend for hundreds of millions of light years. These filaments form towering walls, immense, vast sheets, where galaxies gather in concentrations significantly higher than the cosmic average. And nestled between these imposing filaments and these colossal walls lie the voids, those immense, hollow regions that astonishingly occupy the vast majority of the universe's total volume while containing almost no mass whatsoever. This intricate, large-scale structure of the cosmic web was not immediately obvious. For many decades, astronomers diligently photographed the night sky, meticulously counting and cataloging galaxies. However, the true three-dimensional arrangement, the profound depth and interconnectedness of this cosmic architecture remained stubbornly hidden from their view. Distance measurements, in those earlier times, were often imprecise and unreliable. Galaxies that appeared to be close neighbors in a two-dimensional image might in reality be separated by billions of light years, with one being vastly farther away than the other. It was only when scientists in the 1970s and 80s began systematically measuring galaxy redshifts that the true form of the cosmic web slowly but dramatically began to reveal itself. Redshift surveys, a revolutionary technique, allowed astronomers to precisely calculate the distance to each galaxy. They achieved this by measuring how much the light from these distant galaxies had been stretched towards the redder end of the electromagnetic spectrum due to the expansion of space itself. Suddenly, the vast, previously jumbled distribution of galaxies snapped into crisp, three-dimensional focus. The universe, it turned out, possessed an astonishing and intricate structure on scales that absolutely nobody had ever truly anticipated. The very first major discovery of a cosmic void occurred in 1978, when two independent research teams, working separately, both identified large, underdense regions of space. Following these initial breakthroughs, a flurry of subsequent surveys were launched, each one mapping progressively deeper into the cosmos and consistently revealing an increasingly intricate and breathtakingly complex cosmic web. The Sloan Digital Sky Survey, a monumental project that commenced in the year 2000, generated truly spectacular three-dimensional maps spanning billions of light years across the observable universe. These incredibly detailed maps showcase the cosmic web in truly stunning and unprecedented clarity. The filaments are visible, twisting and branching, like the intricate network of blood vessels within a living organism. The voids in these maps appear as vast, dark, spherical bubbles, some of them an astonishing 500 million light years across. Among the largest and most remarkable structures identified is the Sloan Great Wall, a colossal filament stretching nearly 1.5 billion light years in length. On the opposite end of this enormous spectrum are supervoids like the Eridanus void, which extends an incredible 1.8 billion light years wide, containing even fewer galaxies than our own KBC void. Collectively, these extraordinary features paint a vivid picture of a universe organized on scales far grander and more enormous than anyone had ever predicted. It shows us that individual galaxies are not, in fact, the fundamental building blocks of the cosmos. Instead, the cosmic web itself is the primary, overarching structure, with galaxies merely acting as luminous markers, indicating precisely where the matter happens to concentrate. So, why does the universe organize itself in this particular and peculiar way? The answer to this profound question reaches back to the very beginning of time itself. Immediately after the Big Bang, the universe's matter was not perfectly uniform. Instead, tiny, quantum fluctuations occurring during the universe's first minuscule fraction of a second created subtle variations in density. Some regions were infinitesimally denser than the cosmic average, while others were just slightly less dense. These initial differences were incredibly minuscule, perhaps amounting to only 1 part in 100,000. Yet, even such tiny advantages are profoundly amplified by the relentless and pervasive force of gravity. Over time, the denser regions began to gravitationally pull in even more matter from their surroundings, making them denser still. This created a powerful, self-reinforcing feedback loop. Conversely, the less dense regions gradually lost matter to their more massive neighbors, becoming progressively emptier. Over hundreds of millions of years, this process snowballed, accelerating dramatically. Small clumps slowly merged into larger clumps, which then coalesced into the first galaxies, which in turn aligned themselves into the grand, interconnected filaments. Simultaneously, the underdense regions expanded outwards, evolving into the vast, cosmic voids we observe today. The cosmic web, in essence, is the tangible result of gravity, relentlessly doing its work over the immense timescales of cosmic history. It is the process that transformed, barely noticeable, initial ripples in the early universe into the truly magnificent and grandest architecture in all of existence. Today, these vast voids, astonishingly, occupy roughly 90% of the total volume of space. The intricate filaments and the brilliant clusters only make up the remaining 10% of that volume, yet they contain the vast majority of the universe's total mass. This profound imbalance, this striking disparity, fundamentally defines the very character of the universe we inhabit. We live not in a cosmos that is densely packed with countless galaxies, but rather in a cosmos that is overwhelmingly characterized by emptiness, punctuated only by occasional and relatively rare concentrations of matter. The KBC void in which we reside is merely one such bubble within this vast cosmic foam. But it happens, crucially, to be our bubble, our specific location, and that singular fact makes all the difference for what we observe and how we ultimately interpret the universe around us. Our next chapter will precisely reveal exactly where our galaxy sits within this immense and largely hollow cosmic structure. Our own Milky Way galaxy is not, in fact, located precisely at the very center. However, its position is close enough to the center to be profoundly significant. Meticulous measurements have placed our galaxy somewhere between 200 and 400 million light-years from the void's actual geometric center. Now, that might sound like an absolutely enormous distance, and it most certainly is, by any standard that humans can comprehend or experience. But when you consider that the KBC void extends outwards for a staggering 1 billion light-years in every single direction from its center, our offset becomes relatively small and inconsequential in the grand scheme of the void's immense scale. We are unequivocally situated well within the vast underdense region, enveloped entirely by the void's low-density environment, radiating outwards in all directions. This specific position is not a mere accident or a random occurrence. It carries profound consequences for every single observation we undertake and for every conclusion we draw about the intricate workings of cosmology. If, for instance, our galaxy were located entirely outside the void, perhaps nestled within one of the dense, galaxy-rich filaments, our measurements of the universe's expansion would appear dramatically different. We would almost certainly calculate a slower expansion rate, and consequently, the puzzling Hubble tension would quite simply not exist. Our broader cosmic neighborhood adds another intriguing and complex layer to this already compelling story. The Milky Way is a member of what astronomers call the Local Group, a collection of roughly 80 galaxies, which includes our magnificent, giant neighbor, the Andromeda Galaxy. This local group itself is further embedded within the Laniakea supercluster, a truly massive structure encompassing approximately 100,000 galaxies sprawled across an astonishing 520 million light-years of space. Laniakea, by any conventional standard, is absolutely enormous. Yet, even this colossal supercluster, with its tens of thousands of galaxies, resides entirely within the vast expanse of the KBC void. Take a moment to truly ponder that thought. A cosmic structure containing a staggering 100,000 galaxies is still considered an integral part of an underdense region. The KBC void is so incredibly vast, so utterly immense, that it can effortlessly engulf entire superclusters and still have vast amounts of room to spare. Laniakea, in this context, forms just one part of the sparse population of matter that is scattered throughout the void. It represents one of the rare localized concentrations within an otherwise barren and largely empty cosmic expanse. Furthermore, the local group, our immediate galactic home, is also influenced by another nearby void, known simply as the local void. This void, while distinct from, is nonetheless connected to the much larger and more pervasive KBC void. The local void extends for about 200 million light-years and is situated adjacent to our position. Our galaxy, the Milky Way, is currently rushing away from this local void at that incredible speed of 600,000 miles per hour. This rapid motion is caused by the incessant tug of gravitational forces from denser regions beyond the void's boundary. This particular motion is separate from the overall cosmic expansion. It is what scientists refer to as a peculiar velocity, meaning it directly results from local gravitational effects rather than from the fundamental stretching of space itself. These peculiar velocities significantly complicate our efforts to accurately measure the universe's true expansion rate because they add an extra layer of motion on top of the cosmic expansion signal. Astronomers must meticulously and carefully account for these localized effects. But inside a supervoid, like the KBC, those effects are considerably amplified and consequently much harder to cleanly separate and distinguish. The void's pervasive influence reaches even farther into the cosmos. When scientists measure the motion of galaxies extending outwards to distances of 250 million light-years, they uncover significant bulk flows, large-scale coherent motions that exceed the predictions from standard cosmology. Entire regions of space are moving faster than they should be, flowing in consistent and organized patterns, driven by the void's inherent gravitational imbalance. The KBC void effectively creates a large-scale velocity field, a dynamic and flowing landscape that impacts everything within its vast domain. Galaxies within this void are not merely passively expanding with the universe sitting idly in an empty region. They are actively and dynamically responding to the unique gravitational landscape, accelerating outwards from the underdense region towards the denser structures that lie beyond the void's extensive edge. This makes our local patch of the universe considerably more dynamic and unusual than the calm, uniform cosmos that standard models typically assume. Our specific position inside this void also profoundly affects what we are able to actually observe. Light from distant galaxies on its long journey to our telescopes must travel through the void. That light, during its passage, experiences less gravitational interaction than light that traverses through denser regions. This reduced gravity subtly alters the light's wavelength and its energy. Additionally, the void itself influences the distribution of matter that we perceive. When we look outwards from our vantage point within the void, we essentially see a shell of denser material surrounding us in every direction. That shell manifests as a noticeable concentration of galaxy clusters and filaments at a specific observable distance range. Beyond this shell, the universe eventually returns to a more typical average density. This phenomenon creates a clear and undeniable observational bias. We are not, in fact, sampling a random location in the vast universe. We are, instead, taking our measurements from inside one of its most extreme and unusual features. Living within the KBC void means living with a systematic uncertainty about how truly typical our measurements really are. Every single measurement you have ever encountered concerning the universe's expansion rate might potentially be skewed. Not because scientists have made any errors in their calculations, but rather because we are, quite literally, measuring from within a cosmic whole that subtly distorts the very signal we are trying to detect. The heart of this problem reveals itself starkly when astronomers employ different methods to calculate the Hubble constant. This crucial number precisely tells us how fast space is currently expanding. One method involves meticulously examining the cosmic microwave background, that ancient, faint light from a time when the universe was incredibly young, only about 380,000 years old. This primordial light remarkably encodes vital information about the early universe's density and its initial expansion rate. Scientists then feed this invaluable data into sophisticated cosmological models, and from these, they calculate what the expansion rate should be in the present day. The result, derived from this method, consistently comes out to approximately 67 kilometers per second per megaparsec. To clarify, a megaparsec is a colossal distance, roughly 3.3 million light-years. So this means for every megaparsec of distance, space expands at a rate of 67 kilometers every single second. However, a second, entirely different method focuses on observing nearby cosmic objects with precisely known intrinsic brightness. Specifically, astronomers use what are called type A supernovae and Cepheid variable stars. These particular objects serve as incredibly reliable cosmic measuring sticks because scientists have a profound understanding of exactly how bright they intrinsically should be. By comparing their actual absolute brightness to their apparent brightness as observed from Earth, scientists can precisely calculate their distance. Combining these accurate distance measurements with redshift measurements, which indicate recession velocity, directly yields the universe's expansion rate. This local method consistently produces a noticeably higher number, approximately 73 kilometers per second per megaparsec. The difference between these two highly precise measurements is a significant and troubling 9%. Both measurements, as previously mentioned, are remarkably accurate with extremely small error margins. Both, logically, should provide the same exact answer if our understanding of cosmology is entirely correct. But they simply do not. This persistent discrepancy is precisely what is known as the Hubble tension. It has now reached an astounding 5 sigma statistical significance, meaning there is less than a 1 in a million chance that this disagreement is merely random variation. The KBC void offers a compelling explanation for why these two, seemingly incompatible, numbers fundamentally disagree. When we measure the expansion rate using nearby supernovae, we are, by definition, taking those measurements from within the void. The void's inherently low density translates to less gravitational pull, acting to resist the cosmic expansion. Furthermore, the matter from the denser regions, situated outside the void, exerts a gravitational attraction on the galaxies within it. This adds an extra outward velocity to their motion. Consequently, these galaxies appear to recede at a faster rate than they would if they were located in a typical, average region of the universe. This effect artificially inflates our local Hubble constant measurement. We are not, in this scenario, measuring the universe's true, global expansion rate. Instead, we are measuring the local expansion rate combined with the void's peculiar velocity field, its unique pattern of outward flow. The magnitude of this effect is substantial enough to account for most or even all of the observed tension. When scientists meticulously model how a void of the KBC's size and depth would specifically affect local measurements, they find that it could indeed boost the apparent expansion rate by precisely the amount needed to match our observations. But here is where the implications become genuinely uncomfortable. If the KBC void truly explains our local measurements, then those measurements, by themselves, do not inform us about the universe as a whole. They tell us only about our peculiar and unusual local environment. The cosmic microwave background method, in contrast, remains unaffected by the void because it probes the early universe, a time long before these large-scale voids had even fully formed. That particular measurement, therefore, might represent the truly accurate value for the universe's global properties. This means that many of the headlines you may have seen discussing the accelerating universe and the enigmatic dark energy might, in fact, be describing a predominantly local phenomenon rather than a universal, overarching truth. We have spent decades meticulously building our cosmological models based, in part, on these local expansion measurements. And those very measurements might be systematically biased by our specific location. Some scientists understandably resist this conclusion because it appears to violate the cherished cosmological principle. This foundational assumption posits that Earth does not occupy any special or privileged location within the cosmos. The principle states that the universe should appear roughly the same from any vantage point once you average over sufficiently large scales. Discovering that we reside inside a supervoid, a structure so immense that it significantly affects our fundamental measurements, seems to directly contradict this long-held idea. It suggests that our location is by definition unusual, which, frankly, makes many physicists deeply uncomfortable. Throughout the annals of scientific history, there has been a consistent trend: humanity has been progressively deselected from occupying any special cosmic position. Copernicus famously demonstrated that Earth was not the center of our solar system. Subsequent observations further revealed that our solar system was not the center of our galaxy, and indeed, our galaxy was not the center of anything. The cosmological principle stands as the ultimate expression of this scientific progression. It posits not only that Earth is not at the center, but that there is, in fact, no center at all because every location is fundamentally equivalent. The KBC void challenges this deeply ingrained worldview. If we truly inhabit an abnormally large, underdense region, then our location, by its very nature, is unusual. While cosmic voids are indeed common throughout the universe, most are considerably smaller. Supervoids of this immense scale are exceedingly rare. Finding ourselves, remarkably, inside one raises profound questions. about whether the cosmological principle truly holds true, or whether it is only approximately correct, applying only on scales much larger than previously imagined. Some scientific calculations estimate that in a universe governed by standard cosmology, a void as gargantuan and as deep as the KBC void should be extraordinarily rare. It might represent, as mentioned before, a 10 sigma statistical deviation. In a typical random realization of the universe's structure, you might not realistically expect to find even one such void anywhere within the entire observable cosmos. Yet, here we are, living within one. This suggests either that we are incredibly fortunate, or that the standard model of cosmology is fundamentally flawed in its description of how large-scale structure actually forms. Defenders of the cosmological principle counter-argue that the void does not truly violate the principle. They contend that homogeneity, the idea of sameness, only applies at scales of several hundred megaparsecs or even larger. The KBC void, at roughly 600 megaparsecs across, sits right at the very edge of where homogeneity is theoretically supposed to take effect. Perhaps, they suggest, the universe is simply less smooth at those particular scales than we had previously assumed. Alternatively, some proponents argue that perhaps the void is not as extreme as initial measurements suggest. Different observational techniques can yield somewhat different density contrasts for the void. If the true deficit is closer to 10 or 15%, rather than the more dramatic 20%, then its statistical rarity becomes less severe. These counterarguments aim to preserve the cosmological principle, but they require us to accept that our measurements are less precise than we initially believed. Another line of defense is a form of the weak anthropic argument. This suggests that we should not be surprised to find ourselves in an unusual location because intelligent observers can only exist in certain types of cosmic environments. Perhaps intelligent life requires galaxies to form, and galaxies preferentially form in moderately dense regions rather than in the densest clusters or the emptiest voids. If the majority of intelligent observers were to reside in mildly underdense regions, then finding ourselves in a slight void would not be particularly surprising. However, this argument only holds true if the KBC void is not as extreme as it currently appears. A 20% deficit is more than just mild, it significantly pushes the boundary of what the anthropic principle can realistically explain away. The debate surrounding the cosmological principle is far from settled. Some researchers firmly believe that the void is real and profoundly significant, necessitating either fundamental modifications to our cosmological models or an uncomfortable acceptance that Earth truly occupies a genuinely unusual position. Others contend that the void is merely an observational artifact, or that its properties are not as extreme as initially reported. Still others propose that the principle holds true on even larger scales and that the apparent violation is merely temporary, a localized aberration. Future observations will undoubtedly play a crucial role in resolving this ongoing scientific quandary. Upcoming surveys designed to map the universe to even greater distances and depths will reveal whether large voids are as rare as standard models predict, or whether they are, in fact, more common than expected. If vast voids turn out to be frequent occurrences, it would suggest that the cosmological principle remains intact, but the standard model of cosmology would require significant revision. If, however, they remain exceedingly rare, then we would be forced to explain why we of all places happen to live in one. The very origin of these cosmic voids reaches back to the universe's absolute first moments. The vast, empty regions we observe today began their existence as infinitesimally small quantum ripples in the brief, fleeting instants immediately following the Big Bang. During a period known as inflation, the universe underwent an astonishing, exponential expansion for an incredibly tiny fraction of a second, perhaps lasting only 10 to the power of minus 35 seconds. In this incredibly rapid expansion, these quantum fluctuations, which were initially subatomic in scale, were stretched to cosmic proportions. These fluctuations, these minute irregularities, created slight variations in the density of both matter and energy. In some regions, the density was a tiny bit higher than the cosmic average. In others, it was a tiny bit lower. These initial variations were extraordinarily small, perhaps only 1 part in 100,000. Yet they were profoundly significant, enough to meticulously set the stage for everything that would ultimately follow. After the period of inflation concluded, the universe continued its expansion, albeit at a much slower and more gradual rate. Matter, under the relentless influence of gravity, began to slowly clump together. But this gravitational pulling, crucially, only amplified the initial, barely perceptible density differences. Regions that had begun with a slightly higher density naturally attracted even more matter from their surrounding areas, making them progressively denser still. This established a powerful, positive feedback loop. The denser a region became, the more strongly it gravitationally pulled matter towards itself. Over millions of years, these initially overdense regions gradually collapsed under their own gravity, forming the very first stars, then coalescing into galaxies, and eventually aligning into the grand, interconnected clusters of galaxies. Simultaneously, those regions that had begun with a slightly lower density slowly lost matter to their denser neighbors. As matter gradually drained away, flowing towards the collapsing, overdense regions, these underdense areas became progressively emptier. These underdense regions, through this ongoing process, evolved into the vast, cosmic voids that we observe in the universe today. This entire process is scientifically known as gravitational instability. It is the fundamental mechanism that transformed barely perceptible initial ripples into the dramatic and intricate large-scale structure we meticulously observe throughout the cosmos today. The cosmic microwave background radiation provides us with a direct snapshot, a detailed image of these density variations from a time when the universe was incredibly young, only 3 or 80,000 years old. At that ancient epoch, the variations were still incredibly tiny, visible only as minute temperature differences of about 100 millionths of a degree. But these subtle temperature differences directly correspond to the initial density differences in the early universe. Warmer spots indicated slightly higher density, while cooler spots signified slightly lower density. Satellites, such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the highly advanced Planck spacecraft, have meticulously mapped these temperature variations with exquisite detail across the entire sky. These maps reveal a beautifully modeled pattern of hot and cold spots at various angular scales. This intricate pattern, remarkably, encodes the very seeds of all subsequent structure formation. Scientists can take this primordial pattern and then run it forward through incredibly complex computer simulations to predict how the large-scale structure should appear billions of years later in the present day. These simulations consistently and reliably produce a cosmic web characterized by intricate filaments, brilliant clusters, and vast voids that very closely resembles what we actually observe in our universe. The remarkable match between these theoretical predictions and our actual observations stands as one of the greatest and most compelling successes of modern cosmology. It unequivocally confirms that our fundamental understanding of how gravity shapes the structure of the universe over cosmic timescales is, for the most part, essentially correct. However, a persistent point of contention arises here. These simulations, despite their sophistication, rarely produce voids that are as exceptionally large or as profoundly deep as the KBC void. This is precisely where the current tension in cosmology truly arises. The initial quantum fluctuations that seeded all structure were, by their very nature, random. Therefore, every region of the early universe had some statistical chance of ultimately evolving into either a void or a filament. But probability distributions are incredibly important. Small voids, for instance, a few tens of millions of light years across, should be relatively common as they arise from common, small fluctuations. Medium-sized voids should be less common, and extremely large voids of the KBC's magnitude should be exceptionally rare. The KBC void, as observed, appears to fall squarely into this category of the extremely rare, which naturally raises uncomfortable questions about whether our current simulations are missing something fundamental. One compelling possibility is that the initial quantum fluctuations were not entirely random as conventionally assumed. Perhaps they possessed subtle, underlying patterns that actually enhanced the formation of these large voids. This could occur if the inflationary epoch did not smooth out the initial structure as uniformly as standard models currently assume. Such a scenario would necessitate a significant modification to our understanding of inflation, which itself is already a highly speculative part of cosmology with limited, direct observational evidence. Another intriguing possibility is that the process of structure formation proceeded faster or in a fundamentally different manner than our standard models currently predict. If gravity, for instance, was effectively stronger in the distant past, or if dark matter behaves differently than we currently assume, then structure would form more vigorously, leading to the creation of larger voids and richer clusters. Some researchers have proposed modified gravity theories, where the strength of gravity varies depending on the scale or the cosmic environment. These theories could potentially enhance structure formation and make the existence of large voids more statistically likely. A third option is simply that the universe possesses more inherent variance in its large-scale structure than cosmologists had initially expected, making the presence of large voids less surprising from a statistical standpoint. Each of these explanations, however, requires further and rigorous observational evidence. Observations of more distant voids in other far-flung parts of the universe would be immensely helpful in determining just how truly rare the KBC void actually is. If similar colossal voids are frequently discovered, it would strongly suggest that the standard model significantly underestimates the true variance in cosmic structure. If, however, they remain exceedingly rare, it would strengthen the case for either modified physics or highly unusual initial conditions in the early universe. The quantum origin of these voids is both elegantly simple and profoundly unsettling. It implies that the vast cosmic desert we currently inhabit traces its very beginnings back to subatomic processes that occurred before atoms even had a chance to exist. Randomness at the smallest, most fundamental scales propagated upwards through the expanding universe, ultimately creating the grand, large-scale structure we observe today. The universe's intricate organization is not, therefore, the result of some grand design or predetermined plan. It is instead the inevitable consequence of random quantum fluctuations, relentlessly amplified by the omnipresent force of gravity over billions of years. This profound realization stands as one of the most significant and far-reaching insights of modern cosmology. But it also means that our specific location within this intricate structure is ultimately the result of sheer chance. There is no fundamental reason, no cosmic imperative, why we had to end up in a void rather than in a dense, galaxy-rich filament. We are here simply because the initial conditions in our particular region of the early universe happen to be infinitesimally underdense. That cosmic accident, that roll of the quantum dice billions of years ago, ultimately determines what we perceive when we gaze outwards at the cosmos today. The sheer scale of these empty regions truly dwarfs the human imagination. When you try to picture the universe, you likely imagine a canvas bursting with countless stars and glowing galaxies. But the reality is quite the opposite. The universe is, in its vast majority, overwhelmingly empty. Voids, those immense regions of cosmic desolation, astonishingly occupy roughly 90% of the universe's entire volume of space. Galaxies and their massive clusters are crowded into the remaining 10%, packed tightly into the intricate filaments and colossal walls that encircle and define these voids. This isn't merely empty space in the sense of the vacuum that exists between individual stars or even between galaxies. This is emptiness on a truly cosmic scale, where entire regions stretching hundreds of millions of light years across contain almost no galaxies whatsoever. If you could, theoretically, journey through one of these voids, you would travel for tens of millions of years at the speed of light without encountering a single visible galaxy. The profound isolation would be almost absolute, an experience of pure, unadulterated cosmic solitude. This highly uneven distribution creates a decidedly lopsided universe. The vast majority of cosmic matter concentrates itself within a tiny fraction of the total volume. The filaments, for instance, are bustling, crowded highways teeming with galaxies that frequently interact, merge, and evolve at a rapid pace. Star formation in these dense regions is vigorous and ongoing. Supermassive black holes residing at the centers of these galaxies grow exponentially by accreting material stirred up by frequent mergers. Galaxies collide, sometimes dramatically, triggering intense bursts of new star creation. Meanwhile, the voids are places of profound calm, almost eerie quiet. A few lonely dwarf galaxies drift aimlessly through the vast darkness, separated by truly enormous distances. These void galaxies evolve at an incredibly slow pace, precisely because they rarely, if ever, interact with neighboring galaxies. They tend to be smaller, fainter, and generally less evolved than their counterparts in dense regions. Star formation within them is sluggish, almost dormant. Many void galaxies, astonishingly, still contain large amounts of neutral hydrogen gas, primordial fuel that has yet to condense into new stars. They are, in essence, galactic backwaters, isolated and untouched by the busy and dynamic highways of the cosmic web. The extreme emptiness of these voids inevitably raises questions about just how truly empty space can actually be. Even in the deepest, most desolate voids, dark matter is still undeniably present. Dark matter, that elusive, invisible substance, constitutes about 85% of all matter in the universe. Yet, it does not interact with light, rendering it completely invisible to our telescopes. It is only detectable through its subtle but pervasive gravitational effects. In voids, dark matter is certainly much less concentrated than in the dense filaments, but it still exists at about 15% of the cosmic average density. That might sound like a significant amount, but when spread out over such truly enormous volumes, the actual quantity of dark matter per cubic light year is incredibly tiny. Additionally, voids contain the mysterious dark energy, the enigmatic component that is actively driving the universe's accelerated expansion. Dark energy appears to be uniformly distributed throughout all of space. Therefore, voids possess just as much dark energy per unit volume as the dense regions. In fact, precisely because dark energy does not clump together like ordinary matter it actually becomes the dominant component in voids where visible matter is so incredibly scarce. The intricate interplay between dark matter and dark energy ultimately determines the long-term evolution of these voids. In the early universe, matter, even in the underdense regions, predominantly held sway, and gravity still exerted a significant influence. However, as the universe continued to expand and dark energy became progressively more important, voids began to accelerate their own expansion. This acceleration causes voids to grow faster over cosmic time, gradually encroaching upon and eating into the surrounding filaments. Eventually, if dark energy continues its relentless domination, these voids will consume more and more of the universe. The intricate filaments will thin out, becoming increasingly tenuous. Galaxy clusters will become isolated islands adrift in an ever-expanding ocean of emptiness. Billions of years into the distant future, the universe will become even emptier than it is today, with voids occupying an even larger fraction of the total volume. This future evolution, this destiny of emptiness, appears to be an inevitable consequence given our current understanding of dark energy. The universe's ultimate fate is to become increasingly hollow. Understanding the precise fraction of the universe that is occupied by voids is critically important for accurately interpreting our astronomical observations. When we measure the average properties of the universe, such as its overall matter density or its global expansion rate, we are, by necessity, averaging over both the voids and the filaments. If we fail to account for the fact that most of space is actually void, we might seriously misinterpret what those averages truly signify. For example, measurements of the cosmic microwave background provide us with the average matter density of the entire universe, which is approximately 30% of the critical density required to halt cosmic expansion. However, that average crucially includes both the dense filaments and the sparse voids. The local density within the universe varies dramatically depending on your specific location. In a dense filament, for instance, the matter density might be 3 times the cosmic average. In a void, it might be a mere 15% of the average. These profound variations are of immense importance when we attempt to understand and interpret local observations. The staggering 90% void fraction also significantly affects our searches for rare and dramatic cosmic phenomena. For example, astronomers tirelessly searching for distant supernovae or powerful gamma-ray bursts are overwhelmingly more likely to discover them in the dense filaments where star formation is vigorous and active. Finding these energetic events within the quiet voids is considerably rarer, precisely because voids contain fewer galaxies and consequently less star formation. This creates a clear and undeniable observational selection effect. Most of the truly interesting and dramatic astronomical events occur within the bustling 10% of the universe, not the quiet and desolate 90%. We tend to study the universe from within its most active regions and often inadvertently ignore the vast, empty ones. But these voids are just as much a fundamental part of cosmic reality as the luminous filaments. Understanding them thoroughly is absolutely essential for comprehending the universe as a whole. Among these countless voids, one in particular stands out as especially challenging to our current understanding of physics. The KBC void defies all probability in a way that makes many cosmologists profoundly uncomfortable. Standard cosmology predicts that cosmic structures form through the gradual, gravitational collapse of initial density fluctuations. The larger and deeper a particular structure, the rarer it should statistically be. Small voids, for instance, those measuring a few tens of millions of light years across, are relatively common because they arise from common, small fluctuations in the early universe. Large voids, stretching hundreds of millions of light-years across, are less common as they require larger and consequently rarer initial fluctuations. The KBC void, however, is an astonishing 2 billion light-years across and is 20% underdense. Computer simulations of structure formation, which utilize the lambda CDM model, rarely, if ever, produce anything quite this extreme. When researchers run thousands of simulated universes and meticulously search for voids that are as large and as deep as the KBC void, they find an incredibly small number of matches. The statistical likelihood of such a void naturally existing is extraordinarily low. Some detailed studies have attempted to quantify this improbability. One particular analysis calculated that a void of the KBC's immense size and profound depth represents what is known as a 10 sigma deviation from the expected density. In the realm of statistics, a 5 sigma result signifies less than a 1 in a million chance of it being merely random. A 10 sigma result is almost incomprehensibly unlikely. You would theoretically need to observe trillions of universe-sized volumes just to statistically expect to find even one such void. Yet, as we've established, here we are living directly within one. This is not, by any stretch, a minor statistical anomaly. It is a massive flashing red flag, strongly suggesting that something fundamental is amiss with either our observations or our cherished cosmological model. If the observations are indeed correct, which multiple independent studies strongly suggest, then the model must be missing some crucial component or exhibiting some fundamental flaw. One compelling possibility is that the initial density fluctuations following the Big Bang were not as perfectly smooth as standard inflation models currently predict. If the period of inflation produced more power on large scales than expected, then large voids would form more easily. This scenario would necessitate a significant modification to our understanding of cosmic inflation, which, as mentioned earlier, is already a highly theoretical and speculative part of cosmology with limited, direct observational evidence. Another intriguing possibility is that structure formation proceeded faster or in a fundamentally different way than our standard models currently predict. If gravity, for instance, was effectively stronger in the distant past, or if dark matter behaves differently than we currently assume, then structure would form more vigorously, leading to the creation of larger voids and richer clusters. Some researchers have proposed modified gravity theories where the strength of gravity varies depending on the scale or the cosmic environment. These theories could potentially enhance structure formation and make the existence of large voids more statistically likely. A third option is that the KBC void is not quite as extreme as initial measurements might suggest. Perhaps there are subtle observational biases or systematic errors within galaxy surveys that have caused the void to appear deeper and larger than it truly is. Different research groups, employing different data sets, have measured the void's properties and indeed found somewhat different results. Some studies suggest a 20% density deficit. Others find values closer to 10 or 15%. If the true deficit lies on the lower end of this spectrum, then the statistical rarity becomes less severe, though it still remains a significant challenge for standard models. Confirming the void's exact properties will require even more comprehensive data, particularly deeper galaxy surveys that can map the void's full extent and its precise density profile with much higher precision. Future missions, such as the Euclid Space Telescope and the Vera Rubin Observatory, are poised to provide this crucial and much-needed improved data. The very existence of the KBC void has become a powerful piece of ammunition in the ongoing debates surrounding the standard cosmological model. Critics of the lambda CDM model frequently point to the void as compelling evidence that the model fundamentally fails on large cosmic scales. They argue that our understanding of large-scale structure formation is not yet complete and that the standard model makes incorrect predictions. Defenders of the model, however, counter that rare events sometimes do occur and that finding ourselves in a statistical outlier, while unlikely, is not inherently impossible. They also emphasize that other aspects of cosmology, such as the cosmic microwave background, align exceptionally well with lambda CDM predictions. Abandoning or significantly modifying such a broadly successful model based on one seemingly anomalous structure seems to them premature. Nevertheless, the void cannot simply be dismissed. It is a genuine, observed phenomenon that unequivocally demands a thorough explanation. Either we accept the uncomfortable truth that we happen to reside in an exceptionally rare location, which, admittedly, violates the spirit of the cosmological principle, or we must modify our fundamental models to make large voids more statistically common. This latter option would necessitate changing fundamental assumptions about cosmic inflation, the nature of dark matter, or even the very laws of gravity. Neither option is entirely satisfying, and both represent major shifts in how we fundamentally think about the universe. The KBC void has thus become a critical focal point for cosmological debates, precisely because it sits at the crucial intersection of observation and theoretical physics. It directly challenges our most basic assumptions about how the universe truly works. Until this profound tension is fully resolved, the void remains an enduring cosmic puzzle, a piece that simply refuses to fit neatly into our current, overarching understanding. These immense, empty regions of space astonishingly serve an unexpected but vital scientific purpose. Cosmic voids are, in fact, the very best places in the entire universe to meticulously study the enigmatic dark energy. This is precisely because voids are the only regions where dark energy completely and utterly dominates all other cosmic forces. In dense areas, such as the bustling galaxy clusters, gravity is powerful enough to effectively resist the ongoing cosmic expansion. Clusters manage to hold themselves together gravitationally despite the universe continuously expanding around them. Even on slightly larger scales, within the intricate filaments, gravity still plays a relevant role, actively slowing down the expansion of space in those particular regions. But in the vast, desolate voids, where matter is incredibly sparse, the influence of gravity becomes almost negligible. With no significant gravitational pull to counteract its effects, dark energy solely dictates what happens. The voids expand at a faster rate than the cosmic average, actively driven by dark energy's mysterious, repulsive pressure. This unique environment makes voids natural and pristine laboratories for precisely measuring the strength and fundamental properties of dark energy. Dark energy remains one of the most enigmatic and perplexing components of the universe. It was first discovered in 1998 through meticulous observations of distant supernova. Dark energy astonishingly accounts for about 68% of the universe's total energy content according to our standard models. Its behavior is diametrically opposite to that of normal matter and gravity. Where gravity pulls things together, dark energy actively pushes space apart, accelerating the overall cosmic expansion. The exact nature of dark energy still remains largely unknown. It could potentially be a cosmological constant, an unchanging energy density intrinsically built into the very fabric of space itself. Or it could be a dynamic field that varies in strength over both time and space. Distinguishing between these two profound possibilities requires incredibly precise measurements of how expansion accelerates in different cosmic environments and at different epochs in cosmic history. Voids, due to their unique properties, provide a much cleaner and less ambiguous signal for these critical measurements than the dense, galaxy-rich regions. In dense areas, the ubiquitous force of gravity complicates everything. The local gravitational pull from nearby masses significantly affects galaxy motions, making it exceedingly difficult to cleanly separate the true cosmic expansion from these localized gravitational effects. In voids, however, those complications are minimal. Galaxies within voids move almost entirely due to the overarching cosmic expansion and the dominant influence of dark energy. By precisely measuring how fast voids expand, compared to theoretical predictions, scientists can rigorously test whether dark energy behaves as a constant or whether its strength actually changes. If dark energy is stronger in voids than elsewhere, or if its properties were different in the past, that crucial information would manifest as clear deviations from the expected void expansion rates. Another valuable way that voids help us is through their characteristic shape. Dark energy affects not only how fast the universe expands, but also how it expands in different directions. If dark energy is truly uniform throughout space, then voids should expand equally in all directions, naturally maintaining a perfectly spherical shape. But if dark energy exhibits variations, or if there are other unknown cosmic forces at play, then voids might expand more dramatically in some directions than in others, becoming elongated or noticeably distorted. Observations of void shapes can therefore potentially reveal whether dark energy is truly uniform or whether it possesses some underlying structure. Current measurements generally indicate that most large voids are roughly spherical, which tends to support the idea that dark energy is indeed uniform. But these measurements are not yet precise enough to definitively rule out small variations. Improved surveys in the coming years will provide much better and more accurate shape measurements. The expansion history of voids also inherently encodes vital information about dark energy. Voids have been continuously growing for billions of years, and their current observed size reflects that entire long history. By meticulously modeling how a void should theoretically grow over cosmic time, given different possible dark energy properties, scientists can then compare these predictions to actual observations and thus constrain what dark energy must actually be like. For example, if dark energy was weaker in the distant past and has only recently become stronger, then voids would have grown slowly at first and then significantly accelerated their expansion. If dark energy has been constant throughout cosmic history, then voids should grow at a steady, accelerating pace determined solely by that constant value. Observations of voids at different distances, which inherently correspond to different times in the past, allow us to rigorously test these various scenarios. One particularly useful technique involves precisely measuring void edges. The boundary between a void and a surrounding filament is a critical transition zone where the matter density rises sharply. This boundary continuously evolves over cosmic time as matter gradually drains out of the void and accumulates in the denser filaments. The sharpness and the exact location of this edge depends crucially on how fast the void is expanding, which, in turn, depends directly on the properties of dark energy. By meticulously mapping void edges at different cosmic times and comparing them to detailed simulations, researchers can infer how dark energy has influenced the growth of these voids. Early results from these studies suggest that dark energy has been roughly constant over the past several billion years, which is consistent with the simplest and most widely accepted cosmological models. But ongoing studies are continuously refining these results and actively searching for any subtle deviations that might hint at more complex behavior. Studying dark energy through the unique lens of cosmic voids is a vibrant and active area of current research. Future surveys will undoubtedly discover and meticulously characterize thousands of voids at various distances and sizes. Each individual void provides an independent measurement of dark energy's profound effects. Combining many such measurements will dramatically improve our understanding. If voids ultimately reveal that dark energy is indeed changing, or that it possesses some hidden structure that would truly revolutionize the entire field of cosmology, even definitively confirming that dark energy is constant and uniformly distributed would be immensely important, because it would effectively rule out many alternative theories. Either way, voids are proving to be essential tools for probing one of the universe's deepest and most perplexing mysteries. The KBC void, given its status as the largest and closest supervoid, offers the best possible opportunity for detailed and highly precise study. Its proximity allows for measurements that are simply impossible for more distant voids. Galaxies that form and evolve within these vast cosmic deserts face unique and formidable challenges. Galaxies inside cosmic voids grow up in a state of profound and enduring loneliness. Unlike galaxies found in dense clusters which frequently interact and gravitationally influence their neighbors, void galaxies evolve in almost complete isolation. This fundamental environmental difference shapes every single aspect of their formation and their long-term evolution. Void galaxies typically tend to be smaller and dimmer than their counterparts in the dense filaments. They possess lower masses containing fewer stars and less overall matter. Many void galaxies are classified as dwarf galaxies, barely massive enough to retain their gas against the outward pressure from internal star formation. Their extreme isolation means they rarely, if ever, experience the dramatic galaxy mergers that are so common in dense regions. Mergers are a primary driver of galaxy evolution, triggering intense bursts of star formation and feeding the supermassive black holes at galactic centers. Without these mergers, void galaxies evolve more slowly and consequently remain less developed in their structure and composition. The rate of star formation in void galaxies is generally lower than in cluster galaxies, but there's a surprising and intriguing twist. While most void galaxies form stars at a leisurely pace, a higher fraction of them are classified as starburst galaxies, experiencing intense but short-lived periods of rapid star formation. This might seem paradoxical until you consider their gas content. Void galaxies are often unusually gas-rich, harboring large reservoirs of neutral hydrogen, primordial fuel that has not yet been converted into stars. In dense environments, interactions with neighboring galaxies can strip away this vital gas or trigger star formation, prematurely depleting the gas reservoir. In voids, however, galaxies retain their precious gas for much longer periods. When star formation does eventually ignite, perhaps triggered by internal processes rather than external interactions, there is an abundance of fuel available. The result is an intense starburst, a rapid consumption of gas, before the galaxy settles back into a state of quiescence. The morphology or shape of void galaxies also differs significantly. Most are late-type spirals or irregular galaxies, rather than the smooth elliptical galaxies that are prevalent in clusters. Elliptical galaxies primarily form through numerous mergers, which, as we've noted, are rare in voids. Without these mergers, galaxies tend to maintain their delicate disk structures and their elegant spiral arms. Some void galaxies exhibit remarkably undisturbed morphologies with smooth disk profiles and regular rotational patterns. They have not been battered or distorted by gravitational interactions or tidal forces from close neighbors. This makes them exceptional laboratories for studying how galaxies evolve in truly peaceful and isolated environments. Observations of void galaxies therefore provide a crucial baseline for comparison with the more chaotic and interaction-driven evolution seen in dense regions. The dark matter halos surrounding void galaxies present another fascinating feature. Dark matter, as we know, dominates the mass of every galaxy, forming an extended halo that stretches far beyond the visible stars. In voids, these halos are subject to considerably less external gravitational influence. They tend to remain more spherical and undisturbed compared to halos in clusters, which often get stretched and distorted by the powerful tidal forces from neighboring halos. The simpler and more pristine halo structure in voids makes them easier to accurately model and study. However, the lowest mass halos in voids face a particular challenge. Below a certain mass threshold, which roughly corresponds to a circular velocity of 35 kilometers per second, these halos possess too little gravity to efficiently retain gas. Star formation requires gas to cool and collapse, a process that happens more easily in deeper, more substantial gravitational wells. The shallowest halos simply cannot form stars at all. This explains why voids are not completely filled with countless tiny, dwarf galaxies. Below a certain mass, these halos do exist, but they remain permanently dark, containing only dark matter and no visible galaxies. One puzzling aspect of void galaxies is their chemical composition. Stars, through the process of nuclear fusion, create heavy elements. When these stars eventually die, they release these elements back into space. Subsequent generations of stars then incorporate these newly forged elements, gradually enriching the galaxy's overall chemical composition. This fundamental process is known as chemical evolution. Void galaxies, with their characteristically slower star formation rates, should, theoretically, exhibit lower chemical enrichment compared to galaxies in dense regions. Observations do confirm this to some extent. Void galaxies tend to have lower metallicities, meaning less abundance, of elements heavier than helium. But the difference is not as large as theoretical predictions initially suggested. Some void galaxies, astonishingly, show chemical abundances that are surprisingly similar to galaxies in more normal and densely populated environments. This intriguing finding suggests that chemical evolution is far more complex than simple models predict, perhaps involving significant gas flows both in and out of galaxies that actively redistribute these heavy elements. The evolution of void galaxies over immense cosmic time is an active and vibrant research area. By observing void galaxies at different distances, which crucially corresponds to different times in the past, scientists can trace how these galaxies have fundamentally changed. Early results from these studies suggest that void galaxies have been relatively stable, evolving gradually, without the dramatic transformations that are common in clusters. This inherent stability makes them invaluable for understanding the intrinsic processes that truly drive galaxy evolution without the complicating factors of environmental interactions. Future surveys with improved sensitivity will undoubtedly discover even fainter void galaxies and precisely trace their properties across billions of years of cosmic history. These forthcoming observations will rigorously test whether our current understanding of galaxy formation is truly complete, or whether the unique void environments reveal processes we have previously overlooked. The giant structure that actually contains all these scattered, lonely void galaxies is stranger still. The Laniakea supercluster is a truly mind-bending structure that fundamentally redefines what we actually mean by our cosmic neighborhood. Identified in 2014, Laniakea astonishingly contains roughly 100,000 galaxies spread out across an immense 520 million light-years of space. The name, Laniakea, originates from Hawaiian, and it eloquently means immeasurable heaven, a fitting description given its gargantuan scale. Our own Milky Way is situated on the distant outskirts of Laniakea, forming part of a vast cosmic drainage basin where galaxies collectively flow towards a central, incredibly powerful gravitational attractor known as the Great Attractor. The entire Laniakea structure moves coherently, bound together by these powerful gravitational flows, which on these scales effectively override the general cosmic expansion. Think of Laniakea as a massive watershed, where cosmic matter flows downhill towards the deepest gravitational valley. Except, in this cosmic analogy, the terrain is the intricate curvature of space-time, rather than a literal physical landscape. Here lies a profound paradox. Laniakea, despite its staggering count of 100,000 galaxies, resides entirely within the vast expanse of the KBC void. How can a supercluster, one of the largest gravitationally bound structures in the entire universe, exist inside an underdense region? The answer to this perplexing question lies in how matter density is precisely defined. The KBC void is indeed underdense when compared to the cosmic average, especially when measured over very large scales spanning billions of light years. But it is not, however, uniformly empty. It contains localized concentrations of matter, like the Laniakea supercluster, that are in fact denser than their immediate surroundings. These concentrations are the enduring remnants of the early process of structure formation, like resilient islands of matter that manage to resist being entirely drained away when the void initially formed. They exist as relatively dense patches within an overall underdense volume. From a large-scale perspective, when you average over billions of light years, the entire region is undeniably sparse. But zoom in to a scale of a few hundred million light years, and you will discover significant and intricate structure. This nested hierarchy of cosmic structure is a common feature throughout the cosmic web. Voids often contain smaller filaments, which in turn contain clusters, which further contain groups, which finally contain individual galaxies, which of course contain stars. Structure truly exists at every conceivable scale. The KBC void is primarily defined by the conspicuous absence of rich superclusters and massive galaxy clusters at its very center. The edges of the void, where the matter density gradually transitions to normal cosmic values, are located hundreds of millions of light years away from us. Within that enormous volume, there is still plenty of matter, just not as much as there should be on average. Laniakea occupies a part of that vast volume. It is large when compared to typical superclusters, but comparatively small when contrasted with the void itself. The intricate gravitational flows within Laniakea provide some of the best direct evidence for how gravity fundamentally organizes cosmic matter. By meticulously mapping the velocities of galaxies, both within and surrounding the supercluster, astronomers have constructed a precise, three-dimensional flow map clearly showing how matter moves through space. Galaxies closer to the Great Attractor are falling towards it at a faster rate. Galaxies at the far edges of Laniakea are only just beginning to feel its subtle but powerful gravitational pull. These flows precisely define Laniakea's boundaries. Everything that is moving towards the Great Attractor is considered an integral part of the supercluster. Everything flowing away from it belongs to neighboring structures. The Milky Way's peculiar velocity, our own galaxy's intrinsic motion, points directly towards the Great Attractor, unequivocally confirming that we are gravitationally bound to Laniakea. But Laniakea itself is in turn falling towards something even larger and more massive. The Shapley supercluster, located approximately 650 million light-years away, stands as the most massive structure in our entire region of the universe. It contains tens of thousands of galaxies and possesses a gravitational pull powerful enough to affect everything around it, including the vast Laniakea supercluster. The entire Laniakea supercluster is currently moving towards Shapley at several hundred kilometers per second. This creates a fascinating hierarchy of cosmic flows. Individual galaxies flow towards galaxy clusters. Clusters in turn flow towards superclusters. And superclusters ultimately flow towards even larger gravitational attractors. The KBC void subtly modifies these complex flows by adding an outward component. Galaxies are simultaneously falling towards local attractors, like the Great Attractor, and flowing outwards away from the void's center. The combination of these opposing forces produces incredibly complex and dynamic velocity patterns. Understanding Laniakea's intricate structure and its dynamic motion helps to clarify our precise position within the KBC void. We are not located at the void's absolute center in complete and utter isolation. Instead, we are offset from the center, situated in a moderately dense region that is nonetheless still underdense compared to the cosmic average. Laniakea represents a significant concentration of matter within the void. But it is not, however, substantial enough to entirely eliminate the void's overall underdensity. The apparent paradox resolves itself when you grasp that large-scale and small-scale structures can and do coexist. The void describes the average properties over billions of light-years. Laniakea describes the local properties over hundreds of millions of light-years. Both are real and both are profoundly important for understanding different aspects of cosmology. The precise measurements that have revealed all of this intricate structure rely on a unique cosmic ruler, one that is built from primordial sound waves emanating from the infant universe. These incredible phenomena, known as baryon acoustic oscillations, or BAOs, are essentially frozen sound waves from the early universe, and they have now become the most reliable and accurate ruler for measuring immense cosmic distances. In the first 380,000 years after the Big Bang, the universe existed as a superheated plasma, where matter and radiation were intricately coupled together. Sound waves, veritable ripples of pressure, propagated through this primordial plasma, creating oscillations in its density. When the universe eventually cooled enough for stable atoms to form, these sound waves effectively froze in place. The characteristic distance these waves traveled before they froze left a subtle but measurable imprint on how matter is distributed today. That specific distance is approximately 490 million light-years. It manifests as a characteristic scale in the clustering of galaxies. Astronomers can precisely measure this scale and use it as a reliable, standard ruler because the fundamental physics that created it is incredibly well understood. This cosmic ruler works flawlessly at any distance. Whether you observe galaxies nearby or those situated billions of light-years away, the same characteristic scale consistently appears in their distribution. By comparing the apparent size of this characteristic scale at different distances, scientists can meticulously map how the universe has expanded over immense cosmic time. It's akin to placing identical meter sticks at various distances and then precisely measuring how large they appear. If the universe's expansion is accelerating, distant meter sticks will appear smaller than they should. If the expansion is slowing down, they will appear larger. This ingenious technique is called baryon acoustic oscillation analysis, and it has absolutely revolutionized distance measurements in cosmology. Unlike other methods that rely on the intrinsic brightness of celestial objects, which can be affected by intervening dust or other complications, the baryon acoustic oscillation scale is purely geometric. Using this powerful technique, researchers have meticulously mapped the three-dimensional distribution of galaxies across billions of light years. These maps unequivocally reveal the cosmic web in unprecedented and stunning detail. They also crucially reveal the KBC void. When scientists meticulously analyze galaxy distributions in our local region and compare them to predictions derived from baryon acoustic oscillations, they consistently find a clear and undeniable deficit. The void unmistakably shows up as a vast region where the observed scale of galaxy clustering deviates significantly from what distant measurements predict. This specific mismatch is precisely what you would expect if you were located inside an underdense region. The baryon acoustic oscillations, therefore, provide independent confirmation that the void exists, and they also accurately quantify its depth and its full extent. These precise measurements are by no means simple to obtain. Mapping galaxy distributions requires massive, comprehensive surveys that observe hundreds of thousands of galaxies and meticulously measure each one's precise position and its redshift. Projects like the Sloan Digital Sky Survey and the Baryon Oscillation Spectroscopic Survey have dedicated years to collecting this invaluable data. Processing it requires sophisticated and complex statistical analysis to carefully extract the subtle baryon acoustic oscillation signal from the inherent noise of random galaxy positions. The signal itself is subtle, typically only a few percent stronger clustering at the characteristic scale compared to other scales. But modern surveys are sensitive enough to detect it reliably. They have measured the baryon acoustic oscillation scale at multiple cosmic epochs, effectively tracing the universe's expansion history from when it was about half its current age to the present day. These measurements have revealed something truly surprising. The expansion history appears to deviate slightly from predictions based on the cosmic microwave background. The deviations are most pronounced at low redshift, meaning in recent cosmic history, and they align remarkably with being situated inside the KBC void. Galaxies within the void consistently show redshifts that are slightly higher than what is expected for their distance when using the baryon acoustic oscillation ruler. This observation is entirely consistent with the void's outward flow velocity, adding to the cosmic expansion signal. The baryon acoustic oscillation measurements thus provide yet another crucial piece of evidence for the void's existence and its profound impact on our observations. They demonstrate that the Hubble tension is not confined solely to supernova measurements, but appears across multiple, independent techniques. The precision of baryon acoustic oscillation measurements continues to improve with new and more advanced surveys. The Dark Energy Spectroscopic Instrument, which commenced operations in 2021, is currently mapping tens of millions of galaxies with unprecedented accuracy. These forthcoming measurements will allow for much finer and more detailed mapping of the void structure and its intricate velocity field. Within just a few years, astronomers will know the void's properties to within a few percent uncertainty. That level of precision will either definitively confirm the void as the primary explanation for the Hubble tension, or it will reveal additional complications that will demand further theoretical development. Either way, baryon acoustic oscillations are proving to be an essential and powerful tool for understanding our unique cosmic environment. The very temperature of the universe itself holds a subtle but detectable fingerprint of the void's presence. The cosmic microwave background radiation, that ancient, faint glow from the Big Bang, permeates the entire universe with its ethereal light. Its temperature is remarkably uniform, a mere 2.7 Kelvin just a fraction of a degree above absolute zero. But this apparent uniformity is not absolutely perfect. Tiny, minuscule temperature variations do exist, typically only a few millionths of a degree different from one direction to another. These subtle variations encode vital information about the early universe's structure. Hot spots in this cosmic background correspond to regions that were slightly denser in the primordial soup. Cold spots, conversely, correspond to regions that were slightly less dense. Satellites have meticulously mapped these temperature variations across the entire sky with exquisite precision, revealing the very seeds of all subsequent structure formation. But the cosmic microwave background also reveals something else, something equally profound. It shows clear evidence of cosmic voids. Light from the cosmic microwave background has journeyed for an astonishing 13.8 billion years through countless epochs of cosmic evolution to finally reach us. During that immensely long journey, it passes through all the structures that have formed along the way, including these vast, empty voids. When light enters a void, it experiences less gravitational influence than light that passes through dense regions. This fundamental difference creates a measurable effect known as the integrated Sachs-Wolf effect. As the photon, a particle of light, falls into a slightly less dense region, it gains a tiny amount of energy from the gravitational potential. As it then climbs back out of that region, it loses that energy. Normally, in a static universe, these two effects would perfectly cancel each other out. However, if the void is actively expanding while the photon is passing through it, which is precisely what happens due to the influence of dark energy, then the cancellation is no longer perfect. The photon ultimately ends up with slightly less energy than it started with, which manifests as a subtle but detectable temperature drop. This effect is incredibly tiny, but it is indeed detectable when you average over many voids. Astronomers have meticulously identified the locations of large voids in the nearby universe using extensive galaxy surveys. They then carefully examined the cosmic microwave background temperature in those specific directions and found that on average the temperature is about 10 millionths of a degree cooler than the cosmic average. This correlation is statistically significant and perfectly matches predictions from theory. It unequivocally confirms that voids do indeed affect the cosmic microwave background through the integrated Sachs-Wolf effect. For the KBC void, specifically, the effect should be particularly strong, precisely because of its immense size. Light from the cosmic microwave background passes through nearly the entire void on its way to us, accumulating this subtle temperature deficit over its full billion light-year extent. One of the most intriguing features in the cosmic microwave background is the infamous cold spot, initially discovered by the Wilkinson Microwave Anisotropy Probe. This peculiar region spans about 5 degrees across the sky and appears roughly 100 millionths of a degree cooler than the surrounding areas. It is unusually large and unusually cold compared to the typical fluctuations expected from the early universe. One compelling explanation for this cold spot is that it results from a supervoid situated along that particular line of sight. If a particularly large and exceptionally deep void happens to lie in that specific direction, it could create the observed temperature deficit through the integrated Sachs-Wolf effect. Some researchers have diligently searched for such a void in extensive galaxy surveys and have found weak evidence for an underdensity in that region. However, the connection remains controversial because the supervoid that would be required to fully explain the cold spot would itself be statistically unlikely. The KBC void, importantly, does not align with this specific cold spot. It surrounds us in all directions, rather than appearing in one distinct direction. Its temperature signature is therefore more subtle, manifesting as a modification to the overall cosmic microwave background pattern rather than a localized anomaly. Detecting this signature requires careful modeling of what the cosmic microwave background should theoretically look like both with and without the void. Preliminary analyses suggest the void's presence is consistent with the observed cosmic microwave background, but the signal is not yet definitive. Future measurements with even higher sensitivity should clarify whether the void leaves a detectable imprint on the cosmic microwave background temperature distribution. The temperature measurements also provide crucial constraints on the void's properties. If the void were much deeper or substantially larger than current estimates, it would create a stronger temperature signal that should already be clearly visible. The fact that no dramatic anomaly appears in the cosmic microwave background in our direction places upper limits on how extreme the void can actually be. These limits are consistent with a 20% density deficit extending about 1 billion light-years, which matches other independent measurements. The cosmic microwave background thus provides an independent check on the void's existence and its fundamental properties. It is reassuring that multiple, independent lines of evidence all point to the same basic picture. We reside in a large, underdense region with significant, but not extreme, properties. The very existence of this void has led some scientists to question whether gravity itself needs a fundamental revision. The standard theory of gravity is Einstein's general relativity, which he formulated in 1915. It has, remarkably, passed every single test thrown at it for over a century, from accurately predicting the bending of light around massive objects to precisely explaining the orbital decay of binary pulsars. General relativity forms the unshakable foundation of modern cosmology. But the KBC void challenges this foundation in unexpected and profound ways. If the void is truly too large and too deep to arise naturally in simulations based on general relativity and the lambda CDM model, then perhaps gravity does not work exactly as Einstein predicted on the very largest cosmic scales. Some scientists propose modifying gravity rather than simply accepting that we live in a statistically improbable location. Modified Newtonian dynamics, or MOND, is the most prominent alternative gravity theory initially proposed in 1983 by physicist Mordechai Milgram. MOND suggests that gravity behaves differently when accelerations are extremely small, falling below a certain threshold. At high accelerations, like those experienced on Earth or within the inner solar system, gravity follows Newton's laws and Einstein's corrections exactly. But at the incredibly tiny accelerations relevant for galaxy outskirts and vast cosmological scales, gravity, according to MOND, becomes stronger than general relativity predicts. This modification was originally proposed to explain galaxy rotation curves without the need to invoke dark matter. Galaxies, after all, spin faster than their visible matter can account for. So, either there is invisible, dark matter, providing extra gravity, or gravity itself is fundamentally stronger at large distances. MOND, however, has struggled to explain many other cosmological observations, but it performs better than expected at explaining some features of the cosmic web. In MOND cosmology, structures form more efficiently because the enhanced gravity on large scales pulls matter together more effectively. This naturally produces richer superclusters and deeper voids compared to standard gravity. Computer simulations using MOND gravity naturally create voids as large as the KBC void without requiring unusual initial conditions. The statistical improbability effectively disappears. The void becomes an expected consequence of how structure forms under modified gravity. This is an attractive feature because it resolves the tension between observations and theory without invoking extreme cosmic luck. However, Mundi faces serious challenges. It struggles to explain the cosmic microwave background, temperature fluctuations, which standard cosmology explains beautifully using general relativity. Mundi also cannot easily account for gravitational lensing observations, where massive galaxy clusters bend light from background galaxies. The amount of lensing observed requires more gravity than visible matter, plus Mundi's modification can provide, strongly suggesting that dark matter is still fundamentally needed. Some researchers have developed hybrid models that combine Mundi with a small amount of dark matter, typically in the form of neutrinos. These models, often called neutrino-hot dark matter cosmologies, can potentially explain both the cosmic microwave background and the enhanced structure formation seen in the cosmic web. Another class of modified gravity theories involves changing how gravity propagates over large distances, rather than simply changing its inherent strength. These theories, collectively known as modified gravity theories, introduce additional fields or higher dimensional effects that subtly alter gravitational dynamics on cosmological scales while carefully preserving general relativity's successes on smaller scales. Some of these theories predict that gravity becomes effectively stronger in low-density regions like voids, which would make large voids easier to form. Testing these theories requires precise measurements of how matter moves in voids versus dense regions. If the velocity patterns deviate from general relativity's predictions, it could indicate modified gravity at work. The debate between modified gravity and standard cosmology, with a statistically unlikely void, remains unresolved. Proponents of modified gravity argue that repeatedly finding structures that are too large or too rare, according to standard models, strongly indicates that the models are wrong. They point to the KBC void, the Shapley supercluster, the Sloan Great Wall, and other enormous structures as compelling evidence that structure formation is more vigorous than lambda CDM predicts. Defenders of standard cosmology, however, argue that modified gravity theories have their own inherent problems and that invoking them to solve one puzzle often creates new puzzles elsewhere. They prefer to accept that we live in an unusual location rather than overthrowing a century of successful gravitational physics. Future observations should ultimately help to settle this debate. If large voids and extreme structures turn out to be more common than currently thought, modified gravity becomes more appealing. If they remain rare, the standard model survives, but leaves us with the uncomfortable conclusion that Earth occupies a special and highly unusual location. Either way, the KBC void has become a battleground where fundamental physics is being rigorously tested. The void's existence gravely threatens our fundamental calculations of the universe's cosmic age. The age of the universe is one of cosmology's most important and precisely measured numbers, and the KBC void undeniably puts it in serious jeopardy. Current measurements based on the cosmic microwave background consistently place the universe's age at 13.8 billion years. This number is derived from detailed models of how the universe expanded from the Big Bang to the present day. These models utilize the cosmic expansion rate, meticulously measured from the cosmic microwave background, along with other crucial parameters like matter density and dark energy density. Together, these parameters precisely determine how long ago the Big Bang actually occurred. The result has been independently verified by multiple analyses and is considered highly reliable. But if the local expansion rate is genuinely faster than the cosmic average due to the void's influence, then those models could be fundamentally wrong. Here is the precise problem. If the Hubble constant, measured locally, which is about 73 kilometers per second per megaparsec, truly represents the universe's global expansion rate, rather than a void-distorted, local value, then the universe has been expanding faster throughout its entire history. A faster expansion rate means the universe reached its current size in less time. Calculations show this would make the universe about 8% younger, roughly 12.7 billion years old, instead of the widely accepted 13.8 billion years. That may sound like a relatively small difference, but it creates major and undeniable conflicts with other crucial observations. The oldest stars, found in globular clusters, appear to be about 13 billion years old based on well-established stellar evolution theory. You simply cannot have stars that are older than the universe itself. This direct conflict has led to intense scrutiny of stellar age measurements. These ages are derived from understanding how stars evolve over time. Stars of different masses burn through their nuclear fuel at different rates. Low-mass stars can last for hundreds of billions of years. High-mass stars exhaust themselves in just millions of years. By observing which stars have reached the end of their lives in a globular cluster, astronomers can estimate when all the stars in that cluster initially formed. The oldest clusters show that their most massive, remaining stars are just barely still alive, indicating that these clusters formed about 13 billion years ago. These measurements depend on our understanding of stellar physics, which is well tested, but certainly not perfect. Small uncertainties in how stars burn hydrogen or how they evolve off the main sequence could shift age estimates by hundreds of millions of years. Some researchers argue that if stellar ages are uncertain enough, they might accommodate a younger universe. Perhaps globular clusters are actually 12.5 billion years old rather than 13 billion years old, which would fit with a younger universe. But this requires assuming that current stellar models are systematically wrong in just the right way, which seems rather contrived. Other scientists point out that stellar ages are not the only constraint. White dwarf cooling times provide an independent age measurement. White dwarfs are the dense remnants of dead stars that cool gradually over billions of years. The coolest white dwarfs we observe have been cooling for about 12 to 13 billion years, again suggesting the universe is at least that old. These measurements do not depend on stellar evolution models, making them much harder to adjust. The age tension, much like the Hubble tension, might be resolved if the local expansion rate does not represent the global average. If the void inflates our local measurements, then the cosmic microwave background estimate of 13.8 billion years could be correct. In that scenario, the universe would be old enough for the observed stars and white dwarfs to comfortably exist. This resolution requires accepting that we live in an unusual location, which, as noted, bothers some scientists philosophically, but it avoids requiring major changes to stellar physics or fundamental cosmology. Alternatively, both measurements could be partly right if dark energy has evolved over time. If dark energy was weaker in the past and has recently become stronger, the early expansion would have been slower and the universe would be older than the high local Hubble constant suggests. This scenario is speculative, but not entirely ruled out. The age issue highlights a broader problem in cosmology. Many of the parameters we measure are intricately interconnected. Changing the expansion rate affects not just the universe's age, but also the density of matter, the properties of dark energy, and predictions for structure formation. You simply cannot adjust one parameter without affecting others. This makes resolving tensions incredibly difficult because fixes in one area often create new problems in another. The KBC void offers a way to preserve most of the standard model by attributing discrepancies to our unusual location. But it does not eliminate the age tension completely, because some evidence for the universe's age comes from objects within the void itself. These local age measurements should ideally be unaffected by the void's impact on expansion measurements. Yet, they align more closely with the cosmic microwave background age than the local Hubble constant age. This internal consistency suggests the void explanation, while appealing, may not tell the whole story. Ancient starlight creates another, persistent problem for void-based solutions. The oldest stars in our own galaxy pose a stubborn challenge to any cosmological model that makes the universe significantly younger. These ancient stars, found primarily in globular clusters and the galactic halo, contain very little in the way of metals. In astronomy, the term metal refers to any element heavier than helium. The very first stars in the universe formed from pure hydrogen and helium, elements left over from the Big Bang. They created heavier elements through nuclear fusion and scattered them into space when they died. Subsequent generations of stars then incorporated these newly forged metals, gradually increasing the metallicity of the galaxy. The most metal-poor stars we observe today must have formed very early, before much metal enrichment had occurred. Their ages, therefore, tell us directly how long ago our galaxy originally formed. Measuring stellar ages requires a deep understanding of stellar structure and evolution. Stars spend the vast majority of their lives burning hydrogen in their cores, a phase known as the main sequence. The amount of time a star spends on the main sequence depends critically on its mass. Massive stars burn through their fuel very quickly. Low-mass stars burn slowly and steadily. When a star exhausts its core hydrogen, it evolves off the main sequence, expanding into a red giant and undergoing further evolutionary stages. By observing a cluster of stars that were all born at the same time, astronomers can see which masses have evolved off the main sequence. This specific turn-off point reveals the cluster's age. The faintest stars that are still on the main sequence indicate how long hydrogen burning has been occurring, directly measuring the time since their formation. Globular cluster ages, derived using this method, consistently come out to around 12.5 to 13 billion years. The uncertainty is typically a few hundred million years, mainly stemming from uncertainties in stellar physics, such as how efficiently stars mix their internal material, or how much mass they lose through stellar winds. But these measurements are consistent across many clusters using different techniques. The Gaia space mission has revolutionized these measurements by providing precise distances to globular clusters through parallax measurements. Knowing the exact distance allows astronomers to determine the absolute brightness, which removes one major uncertainty from age calculations. The improved measurements confirm that the oldest clusters are indeed about 13 billion years old. This creates a significant problem if the universe is only 12.7 billion years old, as the high local Hubble constant suggests. You simply cannot fit 13 billion-year-old stars into a 12.7 billion-year-old universe. The numbers, quite simply, do not work. Some form of resolution is absolutely required. Either the stellar ages are wrong, the universe's age is wrong, or both are partly wrong in compensating ways. The stellar age measurements are robust enough that major errors seem highly unlikely. They are based on well-tested physics and confirmed by multiple methods. The universe's age, based on the cosmic microwave background, is also robust, depending on a completely different set of physics. This leaves the high local Hubble constant as the most likely culprit. If that measurement is inflated by the void, the contradiction simply disappears. However, the situation is more subtle. The oldest stars are local objects residing within our own Milky Way. if the KBC void significantly affects our measurements of the universe's properties, should it not also affect our interpretation of these stars? Some researchers argue that it should not, because stellar ages depend on local physics, like nuclear reaction rates, not on cosmic expansion. The age of a star is determined by how long it has been burning hydrogen, which is unaffected by whether we live in a void. Other researchers counter that the initial conditions for star formation in our galaxy depend on when the galaxy formed, which in turn depends on cosmic history. If the void affected structure formation in our region, the first stars might have formed earlier or later than in typical regions. This debate touches on a fundamental question: how much does our local environment truly affect local observations versus cosmic observations? Measurements of distant supernovae and few percent uncertainty. That level of precision will either definitively confirm the void as the explanation for the Hubble tension, or it will reveal additional complications that will demand further theoretical development. Either way, baryon acoustic oscillations are proving to be an absolutely essential tool for truly understanding our immediate cosmic environment. The very temperature of the universe itself holds a subtle but significant fingerprint of the void's presence. The cosmic microwave background radiation, that ancient, faint light from the Big Bang, permeates the entire universe. Its temperature is remarkably uniform, at 2.7 Kelvin, just a fraction above absolute zero. But this uniformity is not entirely perfect. Tiny temperature variations do exist. These are typically only a few millionths of a degree different from one direction to another. These subtle variations encode invaluable information about the early universe's structure. Hot spots correspond to regions that were slightly denser. Cold spots correspond to regions that were slightly less dense. Satellites have meticulously mapped these temperature variations across the entire sky with exquisite precision, revealing the very seeds of structure formation. But the cosmic microwave background also reveals something else, something deeper. It shows direct evidence of cosmic voids. Light from the cosmic microwave background has journeyed through 13.8 billion years of cosmic evolution to reach us. During that immense journey, it passes through the vast structures that formed along the way, including these colossal voids. When light enters a void, it experiences less gravitational influence than light passing through dense regions. This creates a measurable effect known as the integrated Sachs-Wolf effect. As the photon falls into a slightly less dense region, it gains a tiny bit of energy from the gravitational potential. As it then climbs back out, it loses energy. Normally, these effects would cancel each other out perfectly. But if the void is expanding while the photon is passing through it, which happens because of dark energy, the cancellation is not perfect. The photon ultimately ends up with slightly less energy than it started with, which manifests as a subtle temperature drop. This effect is incredibly tiny, but it is detectable when you average over many voids. Astronomers have precisely identified the locations of large voids in the nearby universe using galaxy surveys. They then looked at the cosmic microwave background temperature in those specific directions and found that on average, the temperature is about 10 millionths of a degree cooler than the cosmic average. The correlation is statistically significant, and it matches predictions from theory. It confirms that voids do indeed affect the cosmic microwave background through the integrated Sachs-Wolf effect. For the KBC void specifically, the effect should be particularly strong because of its immense size. Light from the cosmic microwave background passes through nearly the entire void on its way to us, accumulating the temperature deficit over its full billion light-year extent. One of the most intriguing features in the cosmic microwave background is the cold spot, first discovered by the Wilkinson Microwave Anisotropy Probe. This region is about 5 degrees across on the sky and appears roughly 100 millionths of a degree cooler than surrounding areas. It is unusually large and cold compared to typical fluctuations expected from the early universe. One explanation is that the cold spot results from a supervoid located along that line of sight. If a particularly large and deep void happens to lie in that direction, it could create the observed temperature deficit through the integrated Sachs-Wolf effect. Some researchers have searched for such a void in galaxy surveys and found weak evidence for an underdensity in that region. However, the connection remains controversial because the supervoid needed to explain the cold spot would itself be statistically unlikely. The KBC void does not align with this specific cold spot. It surrounds us in all directions rather than appearing in one particular direction. Its temperature signature is therefore more subtle, showing up as a modification to the overall cosmic microwave background pattern, rather than a localized anomaly. Detecting this signature requires careful modeling of what the cosmic microwave background should look like, both with and without the void. Preliminary analyses suggest the void's presence is consistent with the observed cosmic microwave background, but the signal is not yet definitive. Future measurements with higher sensitivity should clarify whether the void leaves a detectable imprint on the cosmic microwave background temperature distribution. The temperature measurements also constrain the void's properties. If the void were much deeper or larger than current estimates, it would create a stronger temperature signal that should already be visible. The fact that no dramatic anomaly appears in the cosmic microwave background in our direction places upper limits on how extreme the void can be. These limits are consistent with a 20% density deficit extending about 1 billion light-years, which matches other measurements. The cosmic microwave background thus provides an independent check on the void's existence and properties. It is reassuring that multiple independent lines of evidence all point to the same basic picture. We live in a large, underdense region with significant, but not extreme, properties. The void's existence has led some scientists to question whether gravity itself needs revision. The standard theory of gravity is Einstein's general relativity formulated in 1915. It has passed every test thrown at it for over a century, from predicting the bending of light around massive objects to explaining the orbital decay of binary pulsars. General relativity forms the very foundation of modern cosmology. But the KBC void challenges this foundation in unexpected ways. If the void is too large and too deep to arise naturally in simulations based on general relativity and lambda CDM, perhaps gravity does not work exactly as Einstein predicted on the largest scales. Some scientists propose modifying gravity rather than accepting we live in a statistically improbable location.